Hi folks, welcome back to Juniper Validated Design for the Metro. Today's session is all about building the JVD. I like to talk about the modernization of the network as a journey. Our customers are at all different stages along this path. The network evolves over time, adapting to new demands of the industry. There's new technologies, services, and protocols that are constantly reshaping the way we design networks. And of course, that includes new physical infrastructure. JVD is very much a reflection of this journey that our customers are on. Let me show you what I mean. We started a few years back with a 4G mobile backhaul reference architecture. First, we built the physical infrastructure consisting of ACX for access and pre-aggregation, MX for aggregation and services edge, and PTX for the core. Then we build out the underlay. In this case, we have ISIS with RSVP MPLS and fast reroute protection. We establish BGP labeled unicast end-to-end to enable seamless MPLS across multiple domains. And here we explain the label impositions and functional operations along the path. Now it comes to the services overlay, which, since this is a 4G reference architecture from a few years back, it includes the more traditional VPN services like L2 Circuit, VPLS, L2 VPN, and L3 VPN. Layer 2 services are further enhanced with Ethernet OAM. Now that the topology is built, we execute the test plan. Every JVD includes a detailed test plan with up to 300 test cases. Shown here, of course, is a drastic simplification, but we're going to analyze all the different failure scenarios and measure how the network responds. We're looking at convergence and resiliency and validating that the devices included here are capable of supporting the given solution. Along the way, we're opening PRs and identifying any feature gaps. We went a step further and updated the topology to compare performance against different protocols, ISIS versus OSPF, and LDP with remote LFA versus RSVP with fast reroute. We validated all these different combinations. Now the network evolves into a 5G xHaul reference architecture, with most of the attention around the front haul performance, since this is the most demanding portion of the architecture. The underlay is updated with segment routing and includes inter-AS scenarios. The physical topology moves from a ring design to a spine and leaf type architecture. It's not mandatory, but it can certainly help accommodate those strict latency budgets associated with 5G. We also introduced the DU aspect. Of course, there's multiple 5G functional splits. We're not trying to show every option here, but the architecture does allow for flexible insertion points, which helps to support a variety of 5G deployments. Services are updated and consolidated into EVPN. This includes particular focus around the HSR to DU connectivity models. Once again, after the topology is stood up, we're going to execute a new test plan written specifically for this solution architecture. One thing I just want to point out, even though the reference architecture comes from mobile operators, the design concepts are in no way exclusive to that particular use case. These same principles can be applied to other provider networks. Now we start to move into even more sophisticated solutions, setting a foundation with transport classes, service mapping, and eventually network slicing. In here, we have seamless segment routing with BGP Classful transport. Now, BGP-CT is a Juniper invented protocol going through the standardization process right now. I'll include some links at the end of this presentation where you can learn more about BGP-CT. In this solution, we create new layers of abstraction with Flex Algo over the same physical infrastructure. These paths are set up by advertising the distinct SIDs across the network. Intra-domain colored tunnels are established with Flex Algo and transport class machinery. BGP-CT delivers the inter-domain capability to stitch the end-to-end color-aware paths. This solution really enhances the popular seamless MPLS with BGP-LU by taking those color attributes which are normally contained within a given IGP domain and allowing those to very easily transcend multiple domains to create a more coherent end-to-end color awareness. And of course, there's other ways to accomplish interdomain traffic engineering. This is just one, and it highlights Juniper innovation. Naturally, the next step comes to turning up our services and then mapping those onto the color transport. This allows us to steer the traffic through the network based on our established SLAs. In the JVD, we create and explain those SLAs, putting ourselves in the position of the customer, trying to solve those critical business needs. Our VPN services include both color aware and color agnostic, which is super important to demonstrate the customer's existing services will continue to operate business as usual, even as we overlay these new layers of abstraction. Here I'm just providing an example showing how simple it is to map our services onto the color transport. The VPN is going to be configured as normal. We simply need to add the extended color community attributes to associate the service with the colored tunnel. For L2 circuit, it's literally 2 lines of configuration shown at the top. First, we create the extended color community and then associate it to the L2 circuit. At this point, you can see from the lower middle output, the L2 circuit itself is now signaled with transport class bronze. On the bottom right, the path selection follows this same logic for both primary and TI-LFA backup. Here's another example where we get a little more tactical with L3 VPN. In this case, we define a policy that maps services at a prefix level. For the example, we're going to map direct and OSPF routes to gold, which is realized as our red paths. The BGP routes matching the particular attributes will be mapped to bronze, which is our blue paths. And in the output below, you can see the effects of this configuration. From the VRF tables, those prefixes are clearly associated to distinct next hops based on our color mapping. Next up, we've executed multiple JVDs focusing on class of service. This is a big topic and very important to take up as a standalone JVD. And again, even though our reference architecture is 5G, the vast majority of this validation is relevant to any provider utilizing class of service, which is basically all of our customers, whether they realize it or not. We do include some topics specific to the mobile operators, such as translation of 4G QCI to 5QI and the characterization of those classes. We establish traffic classification based on 5G traffic patterns. Latency, of course, is a major topic for 5G, so we spend a lot more time in this profile validating if our solution can fit within the given latency budget. On the right, we're validating all the functional aspects of class of service, and this, of course, applies to everyone. We take the same 5G topology shown in the previous JVD in including our flex algos with BGP-CT. It means not only are we validating standard QoS behaviors, but also factoring in color transport. With class of service, we're always looking for deterministic behavior. Things should happen exactly how we expect. In this one, traffic is sent across the network from within each type of VPN services and then mapped onto colored paths. Packets are sent with all different priority markings, and ingress classification is based on fixed or behavior aggregate styles. We verify that traffic lands into the expected queue at each egress point. We want to make sure our scheduling priorities are being honored with the correct bandwidth calculation. We're also going to validate rewrite behavior, taking packet captures at various points throughout the network. We're checking DSCP, 802.1p, and EXP bits wherever applicable. Now, I'm a big fan of never relying on default behaviors. I believe it's better to be intentional about the desired class of service behavior, but we do examine and report on those default behaviors. Our customers inevitably will fall back to default, so it's important that we understand especially any differences between platforms. So as we move from one JVD to another, updating the types of devices. We're going to explain any differences that we discover between those platforms. Code point preservation is another super important topic. We perform packet analysis to make sure the priority bits originally marked are received as expected at the other end. As I mentioned before, the reference architecture being 5G, we really wanted to take a close examination of the front haul latency budget. As part of this, we create different topology permutations to measure latency using real EC-pre traffic streams and perform O-RAN conformance testing with RU and DU emulation. We'll also generate different EC-pre message types and validate performance under stress conditions. All of this and quite a bit more is explained in the JVD documentation, including separate O-RAN health reports. So we've been working with the JVD Next team and recently published 4 Metro JVDs to the Juniper Design Center. Also, about a year ago, we started publishing some tech post articles. So far, we have 5 articles which explain the very first JVD executed on a mobile backhaul reference architecture. Thank you very much for your time. I hope this session was helpful. If you have any questions or feedback, please be sure to reach out.